Okay, so we're going to give this another shot. We just worked through one calculator active problem where they gave us an equation and asked us to analyze some pieces of information that could be determined from that equation. And sometimes it's actually going to be more than one equation. So we're going to go ahead and take a look at another fairly similar problem. This one actually comes from the 2015 exam. It's also question number 1. It tells you it's kind of a question that that the writers tend to enjoy talking about. So in this particular question, here we go. We're going to be looking at the following story, that the rate at which water flows into the drain pipe is given here. So that notice that equation does not tell you how much water, but it's the rate at which water flows. So notice it's a sine wave. And if you recall, sine waves, they increase and they decrease. And so at times, the water is going to be coming in at a higher rate, and at times it would be coming in at a lower rate. And that's going to be measured in cubic feet per hour just during the first 8 hours. And so we'd have to look at, and I don't think it's going to make it very far along this curve. That's all right. And then there's a blockage in that. And so according to this cubic function right here, that's how much the water comes in. So there's going to be some entering the pipe and some leaving the pipe. So the amount of water that's actually in the pipe would be a function of both of those. So kind of a composite. So if this right here, if R of t is our rate, then how much water is in the pipe over that 8-hour period of time? So I'm just going to go ahead and write down the amount, which would be, and of course, if we have the rate and I want to find how much there actually is, then I need to go ahead and take that integral from 0 to 8. But instead of writing the equation out, I'm just going to write R of t dt, because clearly R of t is this entire function, so I don't need to do that. And because this is a calculator active section, I don't actually have to physically go in and think through all of the chain rule implications that would happen from that t squared, because it would get a little bit sketchy. But I'm just going to go ahead and do an fn int from my calculator. Remember, it's fn int y1 comma x comma 0 comma 8. And if you do that, you're going to get 76.570 cubic feet. Now, this piece of data right here, you actually do not write on your test. I'm just telling you that that's how I got that information without physically showing you doing that on my calculator. Okay, so now moving on a little bit further, they're asking you, is the amount of water increasing or decreasing at that time? So the question is more water coming in or is more water going out? So if we were to look at R of 3, which is the amount of water that's entering the pipe, minus D of 3, which is the amount of water that's leaving the pipe, if this was positive, then the amount in the pipe would be increasing. And of course, if it was negative, it was decreasing. But like I mentioned before, this is in the calculator active section. So if I made R y1 and I made D y2 in my calculator, and I just use the evaluate function, y1 of 3 minus y2 of 3, my calculator says it's negative 0.313, or if you, instead of truncating, if you rounded, you would get as negative 0.314. So clearly in this situation, since R of 3 minus D of 3 is less than 0, the amount of water in the pipe is decreasing at t equals 3 hours. And very typically in calculus classes, they don't just want you to say that the answer is this, they want you to explain thoroughly what that is, because that doesn't mean it's always decreasing, but at that particular moment in time, it is decreasing. So moving on to the next portion. They're going to ask you at what time it's at a minimum. Now, that word minimum in calculus should set off bells and whistles for you, that has to do with some kind of an optimization question. So what I'm going to do is I'm going to just go ahead and say, let A of x equal the amount of water in the pipe. Now, if I did that, then that means A of x would be, well, I guess it would be r of x minus d of x, or you could say a of t is r of t minus d of t. But that would tell you the amount at any time t would be the integral from 0 to whatever time you're interested in of r of x minus d of x dt. Plus, excuse me, that actually should not be dt, that should be dx, to be in agreement with what we have. And, but there's one extra little piece of data in there, and they said that when the story began, there was exactly 30 cubic feet of water in the pipe. So I need to know not only what entered and what left, but where we started. And so in optimization, what we want to do is we want to do the derivative. Now, of course, fundamental theorem of calculus would say that the derivative of the integral gives you the original function back. So that would be r of t minus d of t from this upper bound. Of course, when I take the derivative of the 0 portion, it would go to 0, as would this 30. And so if we optimize, we want to set that equal to 0. In other words, where is r of t equal to d of t? And as it turns out, if you do that, you're going to find that that happens at approximately 3.272. So in optimizations, one of the trickiest parts of that is not only are you supposed to check what happens at 3.272. Now keep in mind, this is finding a of that time. So I'm going to actually use this equation. I'm going to go ahead and allow my calculator to do this calculation right here. The integral from 0 to 3.272 of y2. 1 minus y2 plus this 30. And when I did that, I got 27.965 cubic feet of water. And this is the amount of water. But in addition to doing that for a minimum, you're also supposed to check the endpoints. So one of the endpoints, of course, for this particular interval went from 0 to 8. If you try that same exact evaluation, doing an integral from 0 to 0, of course, all you're going to have is the 30 cubic feet of water that started our story. And if you try that again with the number 8, you'd get 48.543 cubic feet. So the amount of water is at a minimum, at t equals 3.272 and is 27.965 cubic feet of water. Now, our last little part is, people get scared by these problems because it looks so much work, but it's actually fairly nice because one of the things they like to do occasionally, in fact, math teachers all over the place like to do this, they'll just go ahead and say, hey, can you at least set it up? This would be a hard problem to do, but it's very easy to set up. And so we've already established that this is the amount of water in the pipe right here, and they say that the water would overflow if it ever reaches 50. So all we have to do is take that equation right here, which is a of t, which is the integral from 0 to t of r of x plus d of x dx. We have our 30. I'm just going to choose to put that in front. Plus 30 is equal to 50. And as it turns out, I don't need to solve that problem. Just have to go ahead and write that little piece of data down, and that would indicate the amount of time when it would overflow. So you can notice that this has quite a lot of similarity between this particular problem and the previous question that we did. So what I would like you guys to do now is I would actually like you to try the 2017 problem number 2. I want to see if you can actually kind of take a look at a similar story. You will also be allowed, in fact, required to use your calculator for some pieces and parts of this question. So I would like you to try the problem and then look up the answer key that I have and score yourself and let me know how you did. You can just upload your work as well as the score that you analyzed to Google Classroom, and I look to hearing from you. All right, good luck.